Okay, two important applications of the acceleration equation comes when we have gears and wheels. So let's start with gears. So the thing to remember is that these points, they have the same velocity, right? So they have the same velocity because they are in contact and they are moving at the same speed. However, they don't have the same acceleration. They have the same tangential acceleration. This vector is the same, but they have different normal accelerations because the normal acceleration depends on the radius, and the radius are different. So that's one thing to remember here. When we have gears, same tangential acceleration, but different normal accelerations. Another important set of problems is when we have rolling motion without slipping. So here we have a wheel, and so this wheel is rolling, and then it has an angular velocity omega and an angular acceleration alpha, right? So the point G, that point moves on that horizontal line. It has a velocity and it also has an acceleration in that horizontal line because that point G is always moving on that horizontal line. What can we say about the acceleration of A? The acceleration of this point. Remember, that point is instantaneously at rest. The velocity is zero, but the acceleration is not. So what we can say is that, so let's just write the equations for the velocity first. The velocity of G is the velocity of A plus omega, and then the position of G relative to A. So if we do the math, that's what we get, that Vg is omega r in the x direction, and that is consistent with the fact that this guy is moving in that straight line, that point G. So how about the acceleration? Well, let's just analyze this way. Just before A touches the ground, so the velocity is going downwards. And right after it's leaving the ground, the velocity is going upwards. So the acceleration have to point upwards, right? So now we can write our acceleration equation, right? So let's write the acceleration of G, right, is equal to the acceleration of A plus the rotation of G relative to A, right? Rotation of G relative to A, that's what that expression is. So let's break this into components. G has an acceleration in the x direction only. A has an acceleration in the j direction, in the y direction. We just said that because just before it's moving downwards and just after it's moving upwards. And then we know alpha, and then we know omega. So this is the rotation of G relative to A. So we can simplify this equation, and then we get that G has an acceleration that is alpha r, and A has an acceleration that is omega squared r. Or we can write those in vector notation as it is written here. These are important equations to remember as we move along and solve more problems. So let's look at one example here. So we have a gear. That gear has an angular acceleration and an angular velocity of 6 radians per second and 12 radians per second. So we want to find the acceleration of this point here at the top. What is the acceleration of that point? So let's start by finding the acceleration of O, which is our G that we normally study in the previous section. The acceleration of O, well, this point is moving in this horizontal line, so it's alpha r. We looked at that, so alpha is given to you at 6 radians per second, and r is 0.3 meters, so you get 1.8 meters per second. So now we can write the acceleration of A, that's the point that we want, that is equal to the acceleration of O plus the rotation of A relative to O. So, and then we break this into components. Acceleration of A is equal to the acceleration of O, which is 1.8 in the x direction. Then this is your angular acceleration minus ck, and then this is this vector from O to A, right? So that's this vector here. And then again, you get that vector here, and this is omega squared. So, and then we can solve this, and we can find our final answer there. Okay, thank you.